Pluto is a far-off and stealthy, more humble planet that was once a part of our nearby planetary gathering. However, progressing and upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They proposed that this cold world is on a possible crash course with Neptune. But how could this actually work, and what might be the consequences of such a titanic event? Are we seeing a beguiling, inestimable peculiarity, or is there something else to this approaching perpetual mishap? Join us as we inspect the probable consequences of a Pluto-Neptune influence. Pluto, a former planet that was later reclassified as a dwarf planet, remains a subject of interest and focus in the vast universe, as shown by ongoing estimates by leading experts. Pluto's orbit is hazardously near Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential hazardous impact between these two planets, which could pose a huge risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our nearby planetary group. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, meandering widely from the almost round orbits of the major planets. What makes Pluto's orbit even more exceptional is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is considerably more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital plan. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does cross Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in an intricate manner. The terms non-synchronous libration and orbital precession, along with the VZK oscillation, are important for this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an additional layer of protection from potential collisions. Another key factor in this situation is the VZK oscillation, named after three researchers, Zell, Kai, and others, who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This gravitational pull influences how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit close to the Sun is so irregular. Despite Pluto's path appearing whimsical, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation demonstrates that, although things in space may seem turbulent and unpredictable, certain patterns and rules keep everything in balance. These factors help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift off course. This three-body problem is critical to understanding how these orbits change because of the way space objects pull on each other. Studying this helps us learn more about Pluto, our local planetary system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually unstable, with minor deviations in starting conditions leading to huge differences over thousands of years. However, these peculiarities in Pluto's orbit have been found to maintain stability over incredibly long timescales. Monitoring this disruption has been crucial. Later automatic examinations have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn also contributes. These studies show that Jupiter's immense gravity is powerful enough to ensure that Pluto stays on a consistent path for a long time. So, perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are essential in maintaining order and stability in space. Without these elements, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could crash into others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it possibly crashing into Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies. Moreover, Pluto's orbit is an ideal example of the unpredictability of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects, like Neptune, pull on one another. By tweaking small details in the simulations, space researchers can see how even minor changes can greatly affect where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession to keep it stable, Pluto's orbit can still be erratic and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. But even with this chaos, Pluto's orbit remains stable over very long periods, like billions of years. This essentially means that Pluto's journey around the Sun has a sort of order to it, even though it seems chaotic at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models depend heavily on the accuracy of initial conditions, and any small mistake or distortion can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So, why are leading astrophysicists recently raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful views on the evolving nature of celestial mechanics and the public's interest in the neglected realms of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment, but as an important adjustment in alignment with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The fascination with these questions keeps space exploration so fascinating. However, despite Tyson's confidence, his thoughts on Pluto's potential impact with Neptune lay out a different picture. His concerns about the future of Pluto's orbit suggest that there might still be more secrets to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the constantly changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The potential for a collision between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges traditional understandings of planetary stability. The idea that two celestial bodies with such incomprehensibly different properties could collide is both unsettling and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would drastically affect their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's enormous mass, powerful gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. The ongoing study of Pluto and its relationship with Neptune provides invaluable insights into the nature of our solar system. Despite Pluto's reclassification as a dwarf planet, it continues to captivate the scientific community with its complex orbit and the potential for future changes in its path. The gravitational interactions between Pluto, Neptune, and the other giant planets have long been a focal point for researchers attempting to understand the finer details of orbital dynamics. These interactions reveal the delicate balance that exists within our solar system, where even seemingly minor forces can have significant long-term effects on planetary trajectories. One important consideration when studying Pluto's orbit is the role of resonance between Pluto and Neptune. As mentioned earlier, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance is a rare phenomenon in the solar system, where 2 bodies' orbital periods are in a simple ratio, helping to maintain stability between their orbits. This resonant relationship is an important safeguard against any potential collisions, as it ensures that Pluto and Neptune never occupy the same region of space at the same time. However, this resonance does not eliminate the possibility of disruptions from other forces, which could alter Pluto's orbit in the future. Another factor that must be considered when analyzing the future of Pluto's orbit is the influence of external forces outside our solar system. While the gravitational pull of nearby planets like Jupiter and Saturn plays a significant role in stabilizing Pluto's orbit, the solar system is not a closed system. Other stellar bodies passing through the outskirts of our solar system could potentially exert gravitational forces on the planets, including Pluto. These external influences, though rare, could cause shifts in Pluto's trajectory, potentially altering its current orbit and leading to greater instability in the future. Moreover, the study of Pluto and its eccentric orbit has broader implications for understanding the evolution of planetary systems. By observing the ways in which Pluto interacts with Neptune and other planetary bodies, scientists can gain insights into how planetary systems form and evolve over time. These insights can help inform our understanding of exoplanetary systems located far beyond our own, offering clues about how other star systems may evolve and what kinds of interactions might occur between planets and other celestial bodies. The long-term stability of Pluto's orbit also ties into broader questions about the fate of the solar system. While the prospect of a Pluto-Neptune collision seems improbable given the current dynamics, it serves as a reminder that the solar system is constantly evolving. Planetary orbits, which may appear stable over human timescales, are subject to gradual changes over millions or billions of years. Understanding these processes not only enhances our knowledge of Pluto, but also helps us better understand the potential futures of the solar system as a whole, including the potential for future planetary migrations or other major changes to the structure of our cosmic neighborhood. These studies also emphasize the need for continued exploration and observation of distant regions in space. While much has been learned about Pluto, many mysteries still remain, particularly regarding its interior structure and surface composition. Future missions, such as the continuation of the New Horizons spacecraft's journey through the outer solar system, will likely provide more data on Pluto and other distant bodies in the Kuiper Belt, enhancing our understanding of this fascinating region of space and offering new insights into the complex interactions that govern the motion of celestial bodies.